Good morning, everyone. My name is Christian Tabedski. I'm in Act 3, which is self-assembly of nanomaterials from the Riggleman Group. And I was fortunate enough to work alongside Patrice Renell in France of 2019, uh, working on modeling atomistic simulations of polyelectrolytes. But today I'm going to be talking about polymer nanocomposites. So polymer nanocomposites are polymers that are impregnated with nanomaterials which imbue additional properties onto the system. Optical properties are interesting because they can deal of optical properties of these nanocomposites are interesting because the spatial arrangement of the nanomaterials within it can affect the properties based off the spatial arrangement of the nanomaterials. So it can affect the absorbance as well as re-emittance of light. And because it's dependent upon nanoparticle control and the arrangement of it within the matrix, an interesting question is, how do you control this distribution? Fortunately, I wasn't the only one at Penn asking this. My collaborators within the compositor group focused on putting nanoplates, which is nanoparticles where the height of the material is shorter than the other dimensions, into polystyrene polymethylmethacrylate domains. In order to drive mixing as well as specific uptake, or as well as uptake into a specific domain, they grafted the nanoparticles with PEG, which has the chemical affinity for polymethylmethacrylate. And what they noticed was the polymers tend to aggregate into these in end-on configurations, so something that we would call strings. And it's a really interesting sort of phenomenon, and we're questioning, all right, why does this happen? And is there any way we can sort of control the average nanoparticle distance? So what I did was use hybrid self-consistent field theory, which allows you to calculate the free energy of the system, as well as get the equilibrium sort of configuration of the system. And on the bottom right is an example image of my system. So we have two nanoparticles approaching each other perpendicularly and on. The green is the nanoparticle core. The yellow is the PEG graft. The red is the PMMA domain, which the PEG has an affinity for. And the PS is the blue is the PS domain. And so what we do is we just vary the distance between the two. And so when it's very close, there's a very there's a very strong repulsion between the nanoparticles, which cause a very sharp free energy rise. And when the particles are very far away in the box, it's essentially like they're in their own world. They don't really interact with each other. The more interesting configurations lie somewhere between the two. So we have the energetic minimum here and the energetic maximum depicted here. And we can see that there's a sort of difference between the two in terms of the curvature of this PS-PMMA interface. So here, it's a very sharp one, or excuse me, not sharp, but there's a large curvature, and it extends also the sort of curvature to the next interface. But when the nanoparticles are closer together in this energetic minimum, there's less of this curvature, and over here, it doesn't inflect back. It has just one smooth sort of curvature to it. And so from this energy plot, we see that there are two sort of configurations nanoparticles would want to take. Either they're far away separated from each other, or they're energetically favored, or they're forming these strings which are energetically favorable. And so when we zoom in onto the minimum, we note a couple of things. There's that sharp rise on the left, as mentioned, and a gentle exit from the well as the nanoparticles separate further. And when we look at the statistics from the experimental data, we see that something similar, the sort of sharp rise for for very close nanoparticle distances, and a gentling leveling out as the distance grows larger. We also note that the average distance between the experiments and the simulations agree quite well. So is there any way that we can affect the average distance? So what we did was we changed the actual matrix. We increased the matrix molecular weight, which in turn had the effect of increasing the lamellar domain sizes. And what we see is that the energetic well, the minimum shifts out to further separation distances, and the well sort of opens up. And that's exactly the same sort of thing that we see in experimental data. We see that the energetic well opens up as you increase the domain, as you increase the size of the lamellar domain. And so overall, we're able to capture the changes in the experimental technique, and we're able to show that the energetic string the nanoparticle stringing is energetically favorable, and that we can reduce the sort of barrier of the system, the energetic barrier here, by going to larger molecular weights, and actually shift out that equilibrium distance by going to larger matrix molecular weights as well. Thank you very much.